In question 4a, we have a transformer operating on a 230 volts mains supply providing a 12 volts output. There are 150 turns on the primary coil. In part 1 we need to find the number of turns on the secondary coil. While using the transformer formula, rearranging for the number of turns on the secondary coil, putting in the values given, gives us 60 turns. In part 2, a number of identical lamps rated at 12 volts 24 watts are connected in parallel across the secondary coil. The primary circuit includes a 630 mA fuse. We need to find the maximum number of lamps that can be supplied by the transformer if it has an efficiency of 85%. Well, power is current times voltage, and the power in the primary is 145 watts. The power in the secondary will be 85% or 0.85 times this, which is 123 watts. Number of bulbs is equal to the total of power divided by the power of one bulb. This gives us 5 lamps. In part 3, the transformer circuit includes a fuse. We need to explain why. Well, the fuse presents excessive current. The fuse prevents excessive current which could lead to overheating. In part 4, we're asked why the fuse is placed in the primary circuit rather than the secondary. Well, if the fuse were placed in the secondary circuit, the primary circuit would still be live if the fuse had melted. In B, we have an experimental arrangement with an aluminium ring around an iron rod which is placed in a coil with an AC supply. In part 1, with reference to the laws of electromagnetic induction, we need to explain why a current is induced in the ring, why the ring experiences a force moving it upwards, and why it reaches a stable position. Well, the AC supply is constantly changing direction, meaning the magnetic field produced by the coil is constantly changing direction. The aluminium ring is within this changing field, and according to Fleming's law of electromagnetic induction, an EMF will be induced in the ring. This produces a current, as the ring is complete, so gives a complete circuit. According to Lenz's law, the magnetic field produced by this current will oppose the change of external field, meaning the field due to the ring is in the opposite direction to the field due to the coil. The two therefore repel. This produces an upwards force on the ring, but the force weakens as the height of the ring increases. The ring will settle where the magnetic force upwards is equal in magnitude to the weight acting downwards. In part 2, we're asked what would happen to the ring if the alternating current in the coil was increased without changing the frequency. Well, if the current was increased, the rate of change of magnetic flux would increase, so the induced current in the ring would increase. This would lead to a stronger magnetic field, so the ring would rise higher, before the force due to the field and the weight of the ring balanced.